Mathematics is a universe of patterns. It's a language that describes the world around us and beyond. At the heart of this language lie functions, powerful tools that capture relationships between different quantities. From the trajectory of a rocket to the growth of a population, functions help us model and understand our ever-changing universe. This essay embarks on a journey into the world of functions. We'll unravel their mysteries, explore their diverse forms, and discover their remarkable applications. Get ready to see the world through the lens of functions. Imagine a machine, a magical box that takes an input and transforms it into a unique output. That's the essence of a function. It's a rule, a set of instructions that assigns to each input value one and only one output value. Think of a vending machine. You input a code and out pops your selected snack. The machine ensures that each code corresponds to a specific snack. That's a function in action. In mathematical terms, we often represent functions using letters like f or g. The input is usually denoted by x and the output by fx or gx. For example, a function f might be defined as fx equals x plus 2. This means that for any input x, the function adds 2 to it to produce the output. The world of functions is incredibly diverse, with different types serving various purposes. Let's explore a few key players. Constant functions. These functions are the epitome of consistency. No matter what input you feed them, they always return the same output. Think of a broken record player stuck on repeat. That's a constant function in action. Mathematically, a constant function might look like fx equals 5, always outputting 5 regardless of the input. Identity functions. Imagine a mirror reflecting your image back to you. That's what an identity function does. It simply returns the input as the output. It's like a faithful echo, repeating whatever it hears. We denote the identity function as ix equals x, where the input and output are identical. Inclusion functions. Think of a treasure chest filled with gold coins. Now imagine picking out a handful of those coins. The inclusion function is like that selection process. It takes a subset of elements from a larger set and maps them onto themselves. For instance, if we have the set of all numbers and the subset of even numbers, the inclusion function would map each even number within the larger set to itself. These examples showcase the versatility of functions. They can be as simple as a constant or as dynamic as a mapping between sets. Just like we can combine ingredients to create delicious dishes, we can combine functions to create new and more complex ones. This process is called function composition. Imagine two machines working in tandem. The output of the first machine becomes the input for the second. That's the essence of composition. We denote the composition of functions f and g as g f f x, meaning we apply f first and then g to its output. For instance, let's say fx equals x plus 2 and gx equals x squared. To find gfx, we first apply f to x, giving us x plus 2. Then we feed this result into g, which squares it, x plus 2 squared. This final expression represents the composition of f and g. However, the order matters in composition. Just like changing the order of ingredients can alter a recipe, switching the order of functions can lead to different outcomes. Section 5, Properties of Composition, Unlocking Deeper Insights. Function composition, like a well-choreographed dance, follows specific rules and patterns. Understanding these properties helps us navigate the world of composite functions with grace. Associativity. Imagine a relay race with 3 runners. The total time remains the same regardless of how we group the runners, A, B, C, or A, B, C. Similarly, in function composition, if we have functions f, g, and h, the order of grouping doesn't affect the final outcome. F, G, hx is the same as f, g, hx. Identity functions. Remember our faithful echo, the identity function? When it comes to composition, the identity function acts like a neutral element. Composing any function f with the identity function either before or after doesn't change the output, ifx equals fix equals fx. It's like adding 0 to a number. The number remains unchanged. These properties are fundamental tools in our mathematical toolkit. They allow us to manipulate and simplify expressions involving function composition, revealing hidden patterns and relationships. Section 6. Restricting functions, focusing on subsets. Imagine a photographer focusing on a specific subject within a larger scene. That's similar to what we do when we restrict a function. We narrow down its domain, the set of allowed inputs, to focus on a particular subset. Think of a function f defined for all real numbers. We might be interested in its behavior only for positive numbers. By restricting the domain to positive numbers, we create a new function, a subfunction, that operates solely within that restricted space. This process is like zooming in on a map. We retain the essential features of the original function, but confine our attention to a specific region of interest. Restrictions are valuable tools when dealing with functions defined on large or complex domains, allowing us to analyze their behavior in a more targeted manner. Section 7. Equality of functions. When do functions match? In the world of functions, two functions are considered equal if they behave identically for every input within their shared domain. It's like having two identical keys that unlock the same door. To determine equality, we need to check two things. 1. Domain. Both functions must accept the same set of inputs. 2. Output. For each input, both functions must produce the same output. For example, the functions f(x) equals sine 2x and gx equals sine x plus x might look different, but they are equal. Why? Because for any input x, both functions produce the same output. Recognizing function equality is crucial for simplifying expressions, solving equations, and understanding the deeper relationships between different mathematical representations. Section 8. Applications of functions, real-world connections. Functions are everywhere in our daily lives, even if we don't always realize it. They're the silent architects behind many phenomena we observe and experience. Physics and engineering. From modeling the motion of planets to designing bridges and airplanes, functions are indispensable tools. Engineers use functions to describe stress, strain, and other physical properties, ensuring structural integrity and optimal performance. Economics and finance. Supply and demand curves, profit functions, and investment models all rely heavily on functions. Economists use functions to analyze market trends, predict future outcomes, and make informed decisions. Computer science and technology algorithms, the building blocks of computer programs, are essentially functions. They take input data, process it according to specific rules, and produce the desired output. From social media algorithms to self-driving cars, functions power the digital world. These examples highlight the pervasive nature of functions. They provide a powerful language to model, analyze, and solve problems across a wide range of disciplines. Section 9. Conclusion. Embracing the power of functions. Functions are more than just mathematical abstractions. They're the building blocks of our understanding of the universe and its intricate workings. From the simplest relationships to the most complex phenomena, functions provide a language to describe, analyze, and predict. As we've explored the world of functions, we've uncovered their diverse forms, their remarkable properties, and their profound applications. By embracing the power of functions, we unlock a deeper understanding of the patterns and relationships that shape our world. So, the next time you encounter a function, don't shy away from its mathematical elegance. Instead, embrace it as a key to unlocking the mysteries of the cosmos and beyond.